G'day, my name is Bruce Robertson and this is Pirate Philosophy. In this series of videos I will be describing an original philosophy, one that you won't find anywhere else, but it is one that is logical, rigorous and dynamic. Welcome. So far in this series of videos we've looked at how, starting from a simple logical processor and sense data and evolution, an organism brain can build up a model of the world using the logical process of pattern identification. And in doing this, it creates a pyramid of patterns by a recursive process of making patterns of patterns until you end up with a model of the world and consciousness and ability to interact with the world. And so we now come up to perhaps a mere few thousand years ago in terms of the evolution and the very start of mathematics. So what is required or wanted from a philosophy of mathematics? Well, a number of things. One, what is mathematics? How is it used? And how does it fit in with the rest of our knowledge of the world, the rest of the philosophy, if you like? And so, having got to the state of evolution of a few thousand years ago, the human brain is very large, it's got a lot of capacity, it can do a lot of processing, and it's got even spare processing time. It got a pyramid of patterns, a model of the world, interacts with the world. But what else can it do? Well, what else it can do is set up what I'm calling an abstract system. And I'm calling it an abstract system to differentiate it from the real system of pattern identification and the model of the world based on sense data, which I'm calling a real system. And then you can have an abstract system which is entirely abstract. It's separate from it. It's got its own processes, logical processes, if you like. And the basis for an abstract system are three things. One, you need symbols, and you need some rules for the manipulation of those symbols, and you need perhaps an axiom or starting point for inferences to be made. And you can set up your own abstract system. I've done so here, I'll show you in a minute, where all you have is some symbols, rules, and an axiom. And for this abstract system that I've created purely for the purposes of this video, it's got four symbols: at, hash, dollar, and percent. And if you want, you can call it the abstract system at, hash, dollar, percent. And the rules of the system are very simple. Rule number one, the string percent at can be replaced by at. Strings of the form percent at or percent hash may be added to each side of any string that has a dollar symbol in it. And this third one is the string at may be replaced by the string or symbol hash, and vice versa. Note that string in this instance refers to a sequence of one or more symbols. So in order to develop theorems from this system, and by theorem I mean something that can be deduced logically from the symbols and the rules and the axiom. And so for this system we can start with an axiom of at, dollar, at. And then we can generate theorems. At, percent at, dollar, at, percent at by rule 2, i.e. adding a percent at to each side of the dollar symbol. and then we can condense the percent at on the right hand side by a simple at, etc. I won't go through it all, but you can end up with the theorem, and these are all theorems. The theorem at percent, at percent, at percent, at percent, at dollar hash. And does it mean anything? Is it pointless? What is the purpose? What makes for a good abstract system? Well, mainly it needs to be a system that one can generate theorems, and secondly it can generate theorems that are interesting. We'll see what interesting means. Perhaps it means that we can correlate some of the symbols with the patterns from the real world, the pyramid of patterns that we have in our own heads. So you're presented with the following data: strings AFG, BRT, LMQ, PPR, AAN, GOJ. And then I ask you which of the following groups or sets fits best with the ones above. And it's 5 different options. And I'm sure you'll have no difficulty in identifying the last one, NPZ, as being the one that fits with that other group. And why? Well, because you will have identified a concept, the idea of threeness. Each of them has 3 different symbols in it. And you've created an idea of 3 symbols, and so the one of the options that has 3 symbols is the one that fits with the others. And this concept of 3 is a pattern. I haven't said anything about numbers, we just have a concept of 3. And this 3 is quite often associated with the number 3 in the logical system of mathematics, but it's a slightly different 3 because one is purely a symbol within the system of mathematics, and the other is a label for a pattern for the concept of threeness. And you can I would distinguish between those by writing out the one as THREE and the other one as a symbol 3. And going back to the abstract system we had of the system at hash $%, these are just purely random symbols, which means that I can simply change them if I want to. So instead of writing at, I can write a 1. So instead of hash, a V, instead of dollar, an equal sign, instead of percent, a plus sign. And when you substitute those in, we get the theorem 1 plus 1 plus 1 plus 1 plus 1 equals V. And V, of course, is the Latin numeral for 5. So effectively what we've got is an abstract system which adds 5 ones together and gets a symbol V or 5. And the thing is with changing those symbols is that those symbols that of 1 and plus and equals and V have meaning within the pyramid of patterns. They're not just, we can map from one to the other. They're not isolated solely within the logical system of the abstract system. And the relationship between the two can be best described as a mapping. And there is a mapping between the symbols of the abstract system and the labels for patterns. So 1 as a symbol we can associate with a concept of oneness. Equals symbol we can associate with the concept of equals, and so on. Examples of other abstract systems would be things like Conway's Game of Life, which has symbols, i.e. just black and white squares. It's got rules, and it's got an axiom, i.e. the starting point, and then it goes through a sequence of different applications of the rules to end up in different configurations, or theorems if you like. So Conway's game of life can be considered to be an abstract system. It's a little bit different to the others because the rules are very specific and they're applied exactly the same each time as it cycles through. Whereas in maths or in the other abstract systems I discussed earlier, there are different rules and you can choose which rule to apply depending on what you want to achieve. And another type of abstract system is the game of chess. It has got symbols, i.e. all the different pieces. It's got rules, which are very specific. And it's got an axiom, i.e. the starting position for all the different symbols. And it's different to the other ones because you have two players, each trying to use the rules in a specific way to achieve a particular end. And each of the different players has a different goal in mind and they are competing each other and it's a game. But again, it's a sort of abstract system. And of course, maths itself is also an abstract system. It has got symbols, rules, theorems, axioms. And going back to the beginning of maths, it would have started with just mere scratchings on a cave wall or a piece of wood or whatever, with a series of 1, 1, 1, 1, just a line scratch. Essentially base 1, arithmetic. And the example I gave at the beginning where you have 1 plus 1 plus 1, etc. equals v, and again, that is base 1 arithmetic where each 1 represents 1 and nothing more. And I'm using base 1 arithmetic here because it's the most obvious, it's the simplest, and it's the basics for it all. And this is philosophy, I'm not doing maths as such, I'm just looking at the foundations of mathematics and what it is and how it works. So I'll just do a few examples using base 1 arithmetic. And of course, within base 1 arithmetic, it's very easy to see the correspondence between the symbols and the reality. You have maybe 3 or 4 ones scratched on a piece of wood, and you maybe have 3 or 4 sheep in a field, and you can make sure that you haven't lost a sheep, and you don't even need to count them. All you need is a correspondence between each symbol of 1 and each sheep in the field. And I want to show how pure mathematics is the manipulation of symbols according to the rules to produce theorems and nothing more. There's no meaning to it, it's just meaningless symbols that are manipulated to produce theorems which may be interesting because they could be mapped onto the real world. And just to show you how these symbols can be manipulated, I'll just go over very quickly a few examples using base 1 arithmetic, where you just have strings of 1s or an empty string. So if you want to add two base 1 numbers together or base 1 strings, there's a simple algorithm that you can use. So I'll put one up here. If you want to add strings S1 and S2 together, put the sum in S3. S1, S2 and S3 are simply labels for strings. That's all they are. So you start off by setting S3 equal to the empty set, nothing. Then you add S1 to the right hand side of S3, add S2 to the right hand side of S3, and then you output S3 as your output. And you can see how that works if you've got adding 1, 1, 1 to 1, 1. Here's a little worked example for you, and then it outputs 1, 1, 1, 1, 1, which is, if you like, interesting because it matches what we know about the real world, where the concept of 2 combined with the concept of 3 gives the concept of 5. And then you can use other, I've just written a few simple algorithms. Subtraction, if you want to subtract S2 from S1, and this one returns a negative sign with the string if S2 is greater than S1, i.e. if you're trying to subtract 4 from 3, it will return -1. So here's a little worked example. Subtracting 1, 1 from 1, 1, 1, 1, outputs 1, 1. And if you try to do the reverse, it outputs negative 1, 1. And negative is just a symbol that means nothing. But in the real world, we can associate that as being negative. And then there's one for multiplication of two numbers, or multiplication, if you like, of the two strings. And note, when I'm doing all this, within the algorithms, there is no use of number. I am merely manipulating the strings, nothing more. Adding a symbol here, taking one off there, that's all. There's no concept of number, it's just a manipulation of strings. And I've got one here for division. The division is obviously, well, we associate it as being repeated subtraction, and so this one uses the subtraction algorithm. If you want to divide S1 by S2, and it's reasonably comprehensive in that it returns a fractional part if the numbers do not divide exactly. I won't go over it all there, but you can see it. It's even got the statement that if S2 is empty, i.e. dividing by nothing, it outputs an error and then it stops. And I've got some examples here of how the different strings change as you go through the algorithm. And here, example, if you want 1, 1, 1, 1, 1, 1 divided by 1, 1, the output is 1, 1 plus 1 over 1, 1. I'm just showing here how base 1 arithmetic can be used with fractions. And you may say, well, what has base 1 arithmetic got to do with ordinary mathematics where we deal everything in base 10? Well, it's quite simple, simply using the manipulation of strings to convert base 1 arithmetic to base 2 numbers. And I've got it here, a little algorithm that'll do that. It converts base 1 numbers to base 2. And there's a little worked example here of how the number 11111 converts to 101 base 2. So they're both 5 in base 10. So there's 5 in base 1 converts to 5 in base 2. And of course, if the base 1 number you're trying to convert into base 2 contains fractions, you can just convert the numerator and the denominator separately. And then having got to base 2, you can, of course, then, there are lots of algorithms around to convert base 2 to base 10. And I've gone over some of this in some detail because there's very little on the internet or anywhere about how base 1 arithmetic works, so I've had to go into that a little bit of detail. But that's the start of mathematics, and it's the start of how to understand mathematics as string manipulation of abstract symbols. And this is also evidenced by the fact that pocket calculators and computers can do arithmetic. They use simple algorithms manipulating strings. The strings mean nothing to them other than the meaning of the symbols within the computers is just how they are applied within the rules of how they manipulate the strings. Otherwise, it's completely meaningless to a computer or a pocket calculator. And so it's only when that output is taken and put across to the pyramid of patterns that we associate in meaning with it. We would associate the concept of numbers, the concept of equals, the concept of everything else. And intrinsically within an abstract system, there is no requirement for what's called consistency, because they're just meaningless symbols. The only consistency comes when you look at how you might map it to the real world. And then you want to say, well, does it make sense within the real world? For example, if the string came along of 1 equals 2, which is quite easy to do using simple algebra, it doesn't map well to the concepts. Well, the concept of 1 is quite different to the concept of 2, and we don't like to think that 1 equals 2, so we put in a rule that you're not allowed to divide by 0. And that makes sense, because as we looked at before, repeated subtraction of 0 will never end. And I put here just a short proof, if you like, that 1 equals 2. And as you can see, the division by 0 is hidden, so that is why there is that rule. We can't divide by 0. And the thing about abstract systems is that they are totally logical and totally rigorous within the rules of the system. It's not like the real world where you've got sense data coming in and it's not quite sure what the sense data is, or you're not quite sure what is the best pattern that fits the data. That's in the real system. In the abstract system, it is totally rigorous. You've got, as I said, you've got symbols, rules, axioms, theorems, and those, it's totally rigid. And if you like, you can think of, that's why a lot of people do think that mathematics is true. That is because within that system, you can prove that, well, we just proved that 1 plus 1 plus 1 plus 1 plus 1 equals 5. You can prove that 1 plus 1 equals 2, and it's all totally rigorous within that system, and some people like to say that it's true. But if it's true, it's only true within that system. It's only true within that particular use of symbols, within those particular rules. And so it's totally rigorous and true, but only within that particular abstract system. And that is the case with maths too. It's what is logically proven within that system is logically true, but only within the system of mathematics. So now we come to the 4 distinct components of mathematics that is the title of this video. Pure maths, applied maths, design maths, and pattern maths. Pure maths is the pure abstract system. It is what we talked about, the symbols, rules, axioms, theorems, totally meaningless. They're just strings, mean nothing else. There's no question about consistency or anything like that. Whatever the rules dictate are the theorems. That is what is within that particular system. It's pure mathematics. What is variable in the system of mathematics is how those rules are applied, in which order, and with what theorems, with what axioms or theories, if you like, if you want to apply it to the real world and you've got simultaneous equations, which rules you're going to use to manipulate those equations to get you to where you want, i.e., x equals 5 or whatever. Second one is applied maths. That's applying it to the real world, where we say we've got area and we want to know what the area of the field is, and we map between particular numbers in the abstract domain with the concept of the area of a field in the real world. And of course, mathematics is incredibly complex. I mean, while you can learn the game of Conway's Game of Life or chess in a matter of a few minutes, it takes 10 or more years in school to learn mathematics, and even then you only learn a small portion of it. It's very, very complex, but extremely useful, particularly in its mapping of statistics, physics, financial world, all those sorts of things. Very, very useful, but very complex. Number 3, design maths. This is where the rules for the mathematical system are chosen, i.e., how the strings are manipulated. what rules you have for solving different equations, whether it's calculus or simple algebra or geometry. What are the rules? How can you match those rules to the real world? Because we have real world, we have concepts of two-dimensional space, three-dimensional space, money, large groups of people, the physics of the real world. And so there is an awful lot in the design of the pure mathematical abstract system so that it models, if you like, the real world, because that's what it does. Mathematics is specifically designed as specific rules that enable one to model the real world. But this mapping, again, is not obvious. Obviously, if you're counting a sheep, you've got 1 + 1 = 2, fine. One sheep plus one sheep equals 2 sheep. But if you've got drops of water, like 1 drop of water plus 1 drop of water, generally doesn't produce 2 drops of water, it just produces one slightly larger drop of water. If you wanted to do the motion of a ball traveling through the air, then you don't want to use statistics or matrices. What you want to use is calculus, and so on. And also within the design of maths, one has to invent new symbols. All the calculus uses different symbols. And also things like the square root of -1, a special symbol that is presented. And that is very useful, but it has to be designed to, and how can you bring it into the system of mathematics without encountering a contradiction which does not match with the real world? And that's quite interesting. And while the square root of -1 is called imaginary, it's really no more imaginary than ordinary integers. You can count sheep using 1, 2, 3, 4, 5, or if you wanted to, you could count them using imaginary numbers of 1i, 2i, 3i, 4i. It makes no difference. And the fourth component of mathematics is what I call pattern mathematics, is where mathematicians, really it's only mathematicians that do this, is they look at the whole system of mathematics, they look at all the theorems, and then they apply a pattern identifying process to those theorems to ask questions like, are there a finite number of prime numbers? Is there a solution to the equation a cubed equals b cubed plus c cubed? Things like that. And mathematicians love playing around with these things as they explore the whole system of mathematics. But that's really not directly related to the other three components of mathematics. And this approach to the philosophy of maths is entirely consistent with Gödel's incompleteness theorem. And his theorem entailed making assumptions of completeness and statements of mathematics and truth, and then showing that making these assumptions resulted in an inconsistency, which then implied that at least one of the assumptions was incorrect, and that the one normally taken to be incorrect is that of completeness, so the mathematics is not complete. And some people consider that to be a problem, but within this approach to mathematics, it's not a problem at all. There's no question about whether the system of mathematics is complete or not. It just is what it is. The only truth that appears within it is when a theorem is generated, and then that theorem can be considered to be true within the system. That's all. And so I'm claiming that this approach to the philosophy of mathematics within the overall philosophy of the pattern paradigm, which I've been describing and continue to describe, is simple, comprehensive, and accurate. And this is in contrast to the standard Western philosophy approach, which is, to say the least, problematic. The difficulty that standard Western philosophy has is that there is no clear distinction between the pure maths and the applied maths. They put the two together and then they try to justify a certain truth of the whole thing. And they try to prove that it's founded on some pure logic or something. And it really doesn't work. Bertrand Russell and others tried to prove that 1 + 1 = 2 was a consequence of pure logic, and of course it didn't work. And other people now try to say that mathematics can be deduced from sets, as those sets are somehow more fundamental than mathematics or integers. All they've really shown is that there is a correspondence between sets on one hand and pure numbers on the other. They haven't shown that one is more fundamental than the other. And as a final note, some of you might find it interesting that the thumbnail and the picture at the beginning of this video was created as a variation of a Mandelbrot set. And I think it's an interesting picture. It's in a way that shows the complexity of mathematics on a very pure level to produce something that is interesting. Well, that is all I have for you today. If you have any interesting comments or questions about today's video, please leave them in the comments section below. And if you would like to continue this journey with me, then please subscribe to my channel, give it a thumbs up and ring the bell. Thank you.